and introduced the concept of partial molar properties in terms of which we describe these kinds of systems. And after we go with that general description and definitions, I said let's take a look at ideal gases, because they're of course the simplest situation we can encounter. And partial molar, I've got here volume, enthalpy, entropy, Gibbs free energy here written out for ideal gases. We'll notice that in ideal gases there is no volume change of mixing or enthalpy or internal energy change of mixing. But we do have, as you would expect, an entropy change associated with the mixing or demixing process. And then any other quantities that have entropic content, like the free energies, that would be like Gibbs energy or Helmholtz energy, those also, of course, are going to have a dependence, even for ideal gases, on composition. And I summarize some of those expressions here. This is from Wednesday. Then also I had started an example at the end on Wednesday which illustrates a classical type of problem that we might encounter with ideal gases, but let me start at the beginning of that example again. It was a bit rushed, and go through it. What we're asked to do here is to calculate the entropy change for mixing 1 mole of air with 2 moles of pure oxygen. And again, we're in the context here of ideal gases. So the diagram of the process is shown below. We're mixing at constant temperature and pressure. And we have system 1 here. I've drawn it that way as 1 mole of air, which we're assuming is going to be 0.78 mole fraction of nitrogen and then 0.22 of oxygen. There are minor other components in air as well, but we're going to treat air as though this were what it was. And we're mixing that 1 mole of air with 2 moles of pure oxygen, and are asked to calculate that entropy change. And so this is a classical, simple type of problem. The first issue of which is just to do a material balance so that we can describe the final mixture, which we see consists of 3 moles, of course, without adding 1 mole to 2 moles. But we'll have to calculate what the final mole fractions are, and calling that final system, system 3. So the mole fraction of nitrogen will be the number of moles of nitrogen over the 3 moles we have in the final mixture. Nitrogen comes only out of the air. So I had 0.78 moles out of that, divided by 3, 0.26, so I would know right away that the mole fraction for oxygen would be 0.74, but I can go ahead and calculate it to verify, yeah, that's how it works out. So I've got the situation described here. Let's write it in here. I got 0.26 and 0.74 for those mole fractions. Then we developed expressions for the entropy change, molar entropy changes of mixing. And of course for demixing, we just put a minus in front of it and we have the same expression. But to carry out the calculations for the entropy change for this process, the first thing we do is to demix. We break it up into steps. The first one of which is to demix the air into pure components. Then we have pure components, which are then in the final step mixed together to get the final mixture. So delta S1 here is demixing my air, and that is going to be, the mixing process is going to be then minus, and then the number of moles that I've got in that system, which is just given to us times R times the summation here, yi log yi. And then if I want for demixing, I put a minus out front there. And then the second step is to mix all of the pure components that I have. That's going to be minus whatever number of moles I have in that final mixture, so N3 times R times that same expression. And if I stick in the numbers here, this will be minus, then I have 1 mole of the air times R, and then 0.78 log 0.78 plus 22 log 0.22. And then for the second step where I'm mixing all of the pure components finally into the mixture, I've got 3 moles of that, so that goes here. And I just plug in once again what I did, and I've got 2 terms here which add up to 1.192 times R, and if I stick in R in terms of joules, then I end up with 9.91 joules per mole K as my final answer for the entropy change of carrying out this mixing process. Any question about this? Your first homework problem on the set that's just being handed out, hope you all get one, is going to be like this. Yeah?
Sorry, can you clarify again why you don't need to include the component 2 in your mixing of the components?
Well, I am. To component, well, how you want to, I'm identifying the components by what they are, nitrogen and oxygen. I haven't labeled them 1 and 2. 1 and 2 is referring to the systems that are being mixed.
Okay.
Anything else? So it's important that you see this simple example, but you can then appreciate that we can solve all kinds of problems like this with ideal gases for mixing, demixing, mixing mixtures, and so on. And it's all just putting together terms of this type, just keeping track of everything. So we might ask ourselves, what if we were mixing things that were not at the same temperature and pressure? Let's say I've got this mole of air at one temperature and pressure, and the moles of pure oxygen at some other temperature and pressure. That would be a slightly more complicated problem, but it just means that you need to do some more work beforehand, and that is you determine the process of mixing. They're almost always adiabatic, and that'll allow you to do an energy balance that lets you get to the final temperature. What you need to do here before you get started with the calculations is to completely describe the final system that you've got. And if we determine then the final temperature, then we do a PVT balance to get the final pressure. We're dealing with ideal gases, so that turns out usually to be pretty easy. Then we can calculate delta S to adjust the original parts to the final temperature and pressure, and then we're off and running just like we had before. Now we've got everything at that final temperature and pressure, so we idealize the mixing process then is occurring at that constant temperature and pressure. Everyone got it? It's interesting to put in here what the thermodynamic work of separation processes is. Separation processes are important. It's a chemical unit operation. It's important to us. We often want to demix air, for example, to get pure nitrogen and oxygen, or we might want to desalt seawater, or we might do things like that. These are all processes of effectively demixing. So it's of interest to be able to calculate the minimum work required to affect this process. And that'll be then the very minimum energy that we would have to put in order to accomplish it. So let's consider that. The separation process, and we're going to consider it as happening at a constant temperature and pressure. If it's a flow process, then we've got from what we studied before that I can write the first law as delta H equal to Q plus W, or the work itself is delta H minus Q. And if it's a constant temperature process, then I can identify Q here as T delta S. So I see the work is delta H minus T delta S, which is just delta G. So the minimum work required for a separation process is the change in the Gibbs free energy for that process. So that's important to know. This was for a flow process, but I might look at the same thing for a non-flow process where now I have the work is delta U minus Q. Again, Q is T delta S. That is then the change in the Helmholtz free energy. So if I want to write that out in terms of the expressions that I have earlier, I've got delta H minus delta PV, but this is a constant this is a term difference at constant temperature, so PV is just RT for ideal gases, so that's going to be 0, and I end up with the same result. In other words, whether it's a flow or a non-flow process, the minimum thermodynamic work required to affect a separation process is delta G. So that's delta G. Work for demixing is going to be minus delta G at mixing. And we know how to calculate that so far, at least for ideal gases. But we need to move beyond that. So let's think about the situation if we have problems like this, but they're going to deal with non-ideal gases. Well, one way to look at it would be the following. We've got this mechanism where we use departure functions to get ourselves in and out, and that means that anything we do can be done as ideal gases. So you could imagine going after a departure function for whatever that initial state is, and that would be the cumulative description of all of the states, whatever, if you have disparate objects that are going to be either mixed or demixed. But you could imagine getting the departure functions for all of those. Then we carry out whatever steps we need to do the mixing, demixing, whatever it is, in the ideal gas state. And then we have to get ourselves out at the end, back to the real state, which may be multi-component. So at least you can see how that might work. But if we want to get these departure functions, what we need are PVT-Y descriptions of the non-ideal gas multi-component systems. Generally, we don't do it this way. That's a good way we could think about that we might be able to accomplish it in that manner, but it's generally more efficient for us to look at a description of non-ideal gas systems that are multi-component that we, say, get out of the laboratory. And then from that, extract functional representations for the various partial molar properties, and then put them together in this easy way to solve mixing or demixing problems. So what we would go after here is from laboratory data, we want to be able to ultimately get expressions here for the partial molar volume, for example, intensive property of the system as a function of temperature, pressure, and composition, or partial molar enthalpy here as a function of temperature, pressure, and composition, and so forth for all of these components. Now we can do that in general because it's possible for us to make very accurate measurements of, let's say, the volume change of mixing. They have digital densitometers now that can give you the density of a material to 4 decimal places. So those are quite easy measurements to make in the laboratory. And as far as getting things like the partial molar enthalpies, we can do very accurate microcalorimetry where we can make measurements of the heat effects associated with mixing processes and therefore get information that will give us the molar enthalpy or molar enthalpy change of mixing, which we call the heat of mixing. And then from there, deduce what the partial molar enthalpies are. And you'll see that in your second homework problem, how we do that with a particular very important system of sulfuric acid and water. So the way it would work would be something like this. The volume of the mixture here is expressed in terms of the partial molar volumes. So if we have these expressions, we can calculate that. Volume change of mixing. The volume change of mixing is just the moles 10 times the molar volume change of mixing, and that is expressed in a general way here in terms of the partial molar properties. Just equal here to the mole fraction. I've written that as Y, assuming it's gases. If it was liquids, I would write it as X's, as I indicated on Wednesday. Multiplied times the difference between the corresponding partial molar volume, in this case, minus the pure component molar volume. And I can do the same thing for the enthalpy and then get expressions for the partial molar enthalpies ultimately out of the measured heats of mixing from calorimetry. We will see this as we go. Let's stick with gases for the moment and see how we might get a description of the PVT-Y behavior of gas mixtures that happen not to be ideal gases. There's a little bit of reading here. Going to have smatterings of reading along as I go through this lecture, and I think I've given you a cumulative reading assignment that I posted today, so you can see that. So what we're after here is the volumetric or PVT-Y behavior of non-ideal gas mixtures. Now the way we describe those are the same way we would describe pure component mixtures, but we let the constants be functions of composition. So let's look first at the way it looks when we are dealing with the cubic equations of state. And the cubic equations of state that we have seen in this class are the Van der Waals equation and the Red-Kwong equation and the Peng-Robinson equation. So I'm talking about those kinds of things now. So if I write it out, let's just say for Van der Waals. The expression that we have is P is equal to RT over V minus B minus A over V squared. So that's the expression that we're familiar with for a pure component. And A and B are the constants that describe that, and we saw how to get those out of critical point information. But now what I'm saying is that these constants, we'll use the same equation to describe the mixture, but these constants now, I'll put a subscript M there, they suggest that those are functions of composition. So AM and BM are functions of composition. Well, what functions? Van der Waals proposed that since we have a preponderance of two-body interactions involved in this non-ideal gas behavior, that it makes sense to express these mixture constants as quadratic functions. And so he wrote, I'll write it out for a binary. Write it a little bit better here. He suggested that the mixture A should be A, and now I'm going to give it a double subscript. Let's do it this way. Y1 squared A11 plus 2A12 times, I'll get her here. 2Y1 Y2 A12 plus Y2 squared A22. Now the A11 and A22 are the pure component 1 and pure component 2 values for the Van der Waals constant A. But A12 here is a new animal that I'm going to say something about here in a moment. But the other constant also would be assumed to be a binary function, so I write that out the same way. Y1 squared B11 is 2Y1 Y2 B12 plus Y2 squared B22. So what we need to do here is deal with these guys, these cross constants. Now A and B have physical significance. Remember, A refers to the attractive energetic interactions between a pair of molecules as they come together. And given that that is the situation, it makes physical sense. You may remember from physical chemistry, the Berthelot's law that gives us a geometric mean mixing rule for energy parameters. In any case, whether you do or not, this is the way we do it. So we use a geometric mean for that energy parameter. And for B12, we'll use the arithmetic mean. Remember what B represents. It has units of volume, and it represents the actual molecular volume, or the so-called co-volume. So that we just take as the arithmetic average of the two pure component values. These things are examples of what we'll see more of as we go forward. These are called mixing rules. Now, if I plug the mixing rules back up into these expressions, I'll end up with the effective expressions for the mixture constants in terms of the pure component constants by themselves. And sticking with the idea of it being a binary, AM turns out to be Y1 times the square root of A11 plus Y2 times the square root of A22 quantity squared. And you can see that yourself. If you plug in the mixing rule into the binary expression above, then this is what it boils down to. And Bm works out to be just the mole fraction average. But you can see that if I have these, now I have an expression for what I asked, what I wanted. I have a PVTY equation of state for this binary mixture. And this can be generalized. You can perhaps see how you would do that to any number of components. You would stick with the binary expressions and the mixing rules would stay the same. This would be the same procedure you would use if it were a Red-Kwong equation. A slightly different algebraic form, but it has just the two constants A and B. There would be the Red-Kwong constants in that instance. But this procedure would be identical. I need to say something a little bit different for Peng-Robinson, and then make a comment about that. Peng-Robinson equation has an A and a B, and those would be the same. So AM and BM for Peng-Robinson obtained in the same way. I'm just going to write it like that. But that isn't all there is to the Peng-Robinson equation. Remember, there's a third parameter there. What is that third parameter, remember? Eccentric factor, right? So we have a third parameter, the eccentric factor, and so what do we do with that? Well, what is done is, operationally, we just take it as the arithmetic mean of the two acentric factors of the pure components. This is no physical basis for this at all. It's just an ad hoc procedure, which gives you an idea of what I'm going to say about using Peng-Robinson for mixtures. That isn't all there is to it. We've also got in that Peng-Robinson equation, we have a reduced temperature all by itself, which means we have to have a critical point temperature. And so that would require some critical point temperature effective for the binary composition of 1 and 2, and we take that as the arithmetic mean TC1, TC2. Again, semi-ad hoc. So these are not the best. It's the best we can do, but it's not very good. So the end result is not very good for mixtures. In other words, we can't retain the same kind of accuracy that we have when we're describing the pure component behavior by the Peng-Robinson equation. Peng-Robinson is quite miraculous. In terms of the 3 parameters, we're able to get a reasonable, good enough for design purposes, description of the PVT behavior all the way through to the liquid state. But that power is somewhat lost when we try to use Peng-Robinson to describe mixtures.
You said something about the algebraic form of AM and BM being different for Red-Kwong. Were you talking?
They're exactly the same. It's just that the constants for the pure components are different, obviously.
Okay, yeah.
Yeah.
Okay.
Anything else? So I want to now take another approach, which is for gases, highly recommended, and that is use a virial expansion-based description. And this is now, as soon as we talk about virial equations, we're limiting ourselves to gases. Well, that's kind of what we've been talking about, but just a reminder that that's rigorously true. And the way we have implemented the virial expansion is through the use of the Pitzer format, which is a truncated pressure explicit virial expansion, where we wrote out that the volume of, now it's going to be the volume of a mixture, is RT over P plus the relevant second virial coefficient, but now that's going to be the virial coefficient here, sub m. Now, completely rigorously, you know that B embraces only binary interactions. So now with complete rigor, we can write out the effective mixture second virial coefficient as a binary function of the mole fractions. And again, for a binary system, I can write this out as that way. For any number of components, I can just write the general binary expression, so Bm is just going to be this double summation here, yi, yj, bij. So you just have more and more terms like that. We're going to pretty much stick with binary systems, and there'll be some discussion about going to more components, but for the most part, we're going to be dealing with binary systems. All right, so if I write this out, then it calls for a cross virial coefficient. And there's a, how would I describe it, a significant database for B12 as a function of T for a number of small gas type pairs. And that can be found in the literature. We could also estimate it when it's appropriate using the Abbott correlations. Not gonna rewrite that down, but remember what that was. The Abbott correlations give us the second virial coefficient for a pure gas, that's what we've seen so far, as a function of the reduced temperature. But now, if we're gonna do that, then we use, again, an effective critical temperature for the pair, say, consisting of molecules 1 and 2 as the geometric mean. And there is some scientific basis behind this, which I don't think we need to discuss. It reflects the dominance of dispersion force interactions over other types of molecular interactions. But in any case, this is what is used, and then we can use the added correlation to get a reasonable estimate for the cross-virial coefficient. Once we have that and the pure component coefficients, we can go back, plug them in to get the relevant virial coefficient for the mixture. Yeah.
In the summation, is that YI, YJ?
Yeah, YJ.
Okay.
Is this is Virial better than Peng-Robinson in this context, or?
I would say yes. It's much simpler, but the Peng-Robinson complexity is not worth it anymore because we've kind of lost its power.
Is it better or about the same as the van der Waals?
That would be a close call. But you can see some advantages of using this virial expression perhaps because we've got rigorous binary interactions here. And then there's a systematic way of improving it. If we have, these are very rare, but if we had ternary, that is third virial coefficients, they would be functions of y1, y2 squared, or y2, y1 squared, or y1 cubed, or y2 cubed. So those would be more complicated. And their database for those third virial coefficients are very rare. But who knows, we might be able to get them in the future, and we have a systematic format here for improving this representation. So there's some advantage in that. Well, we've got now, in principle, at least here, a description of the PVTY behavior of real gas mixtures. So the next issue is then having that, how do we extract expressions for the partial molar volumes? See how much room I got there. Let's go to another page. So this is what we want. We want to get expressions for those guys. So let's start out by writing the expression, and I'm going to do it with this virial expansion-based representation, which is by far the simplest one to work with. And that isn't to say it wouldn't be possible to go back to things like van der Waals or Red-Kwong, but that is much more messy. So let's write it out for a binary. Well, let's remember what this is. That's the derivative of the extensive volume here with respect to the relevant mole number at constant temperature, pressure, and all mole numbers not equal to that one. In other words, at constant composition. So that's my defining equation for the partial molar volume, and that's what I would like to be able to extract out of this expression. Well, right away, we can't just do it. We have to do some things. So I have to multiply by n, number of moles, to get the extensive property. And at the same time, let's put the y's in terms of n's. So this is just the mathematical procedure. So we'll get V here, that's the volume of the mixture, is going to be n times RT over P, plus then n, and now I'll write y1 in terms of n's, and that would be then n1 over n squared, B11, plus 2, now I've got n1 over n, times n2 over n, B12, plus I've got to remember to put the N out in front of there, that's so.
Would it be 2N?
Now let me stand back and make sure I've got it all. Yeah, so I've multiplied by N, and then I've replaced all the mole fractions with what they are in terms of N over N. N1 over N or N2 over N. So that's,
He is missing a 2.
what?
Are you missing a 2 in the middle? Next to the 2?
Oh, thank you. It's so easy to screw that up, so I'm counting on you for that. How about now? So now we have to differentiate this with respect to N1 if I want V1. So if I go through that process, I'm going to have, doing that differentiation is going to be RT over B. And here I don't want to screw this up, so let me be very careful. Okay, anybody see anything that looks okay to me? And the next step in this systematic procedure is then to put it back in terms of y's. Now, if it, that means that the powers of n have to work out so I can change everything back into mole fractions, and if you've done this and it looks like that's not the case, you've made a mistake. So let's do that. I can write everything back in terms of y's, and that gives me I've also put everything in terms of y2 at this point. And then it turns out to be convenient